Greetings and welcome to the Stoichiometry Vodcast with Ms. Carr. We are starting a new unit, and so I want you guys to be um, fresh and alert and pay attention to everything that I have to say because this can be a bit overwhelming, particularly if you've been struggling with the last two units. So if you get stuck anywhere, please feel free to pause or rewind, write down a timestamp on the video and refer to it when you come to me for tutoring. This is a topic that might require more vodcasts, and so we will break it into at least 15-minute sections so that you won't have to watch huge long videos or anything, but we'll use some additional podcasts for examples of stoichiometry. And we started stoichiometry talking about proportional relationships. And the best example of this is simply a recipe, because this is really all a chemical equation is a recipe for how to make different chemical products, right? And so it is a recipe. It's not like a recipe, it is a recipe. And so that's why I choose to use a recipe as an analogy, or for example, here is a different cookie recipe than the one that I gave you to work on for the last activity. This recipe actually makes 5 dozen cookies, where the last recipe I gave you made 2 dozen. And so we're going to take a look at some of the differences between this recipe and the last recipe we looked at, but we're also going to look at how we can figure out how many of something, how many of a product we can make given a number of ingredients. For example, if you have 5 eggs, how many cookies can you make? And so looking that you have 2 eggs per recipe or per batch of 5 dozen cookies, we have this equality of 2 eggs equals 5 dozen. So we can use our dimensional analysis here to cancel out our eggs and be left with 12.5 dozen cookies. And if you understand how we did that, and at this point you should, this should be a fairly simple conversion for you. So dimensional analysis plays a huge role in our proportional relationships, and so it's very important that you are able to do this dimensional analysis easily and correctly. So this is the ratio of eggs to cookies. This 5 dozen equals 2 eggs. And so those ratios are going to become very important when we look at the recipes and when we look at the chemical equations as well. Okay, so if we take a look at what stoichiometry is, besides a really silly word, stoichiometry is the mass relationships between substances in a chemical reaction, and it's based on the mole ratio. Okay. The mole ratio is indicated by the coefficients in a balanced equation. So here you have two magnesiums. That can be 2 particles of magnesium or 2 atoms of magnesium. And then you have, of course, the implied 1 here. Remember, chemists don't like 1s, so we tend to drop them. And then 2 for magnesium oxide. So this is actually the mole ratio. This means that 2 moles of magnesium combined with 1 mole of oxygen will lead to 2 moles of magnesium oxide. So while we didn't exactly go over this specifically when we were looking at balancing equations, that's what this coefficient means. It means that there are 2 parts magnesium for every 1 part of oxygen, and then that leads to 2 parts magnesium oxide for every 1 part of oxygen, or 2 parts of magnesium. Okay, so taking this a bit further, we want to specifically talk about our coefficients. Now, there's a number of things that coefficients can stand for. They can stand for number of moles. They can also stand for particles, or atoms, ions, or molecules. And they can also stand for the volume of gases. Okay? For example, if you say 2H2 plus O2 will react to form 2H2O. So hydrogen gas and oxygen gas will form 2 molecules of water. So this equation can be interpreted as 2 moles of hydrogen, 1 mole of oxygen, and results in 2 moles of water. So that's 2 to 1 to 2 is the mole ratio. Or you could say it means 2 molecules of hydrogen and 1 molecule of oxygen will lead to 2 molecules of water. Or you could say that 2 volumes, say 2 liters of hydrogen, and 1 liter of oxygen will form 2 liters of water. Okay. What you cannot say, and this is very, very important to stoichiometry, you cannot say that it's 2 grams of hydrogen, 1 gram of oxygen, and 2 grams of water. Okay, do not do this because this will lead to you having all sorts of other problems. Now, we're going to talk about ways for you to remember not to do this here in a moment, but you cannot say mass is um, related to those coefficients because these coefficients do not relate to mass at all. So, the steps of stoichiometry. What is very important is that you are able to write a balanced equation. If you are still struggling to write balanced equations, please come and see me. Scroll down in our video library and find the vodcast on writing balanced equations and continue to work on that. Identify what you know and what you don't know. It's very important that you know what you're working with and know what you're working towards. Just like in dimensional analysis, you need to know what your end goal is, and you need to start with what you do know. So, identifying your knowns and unknowns is very important. The next, you line up your conversion factors, making sure that your conversion factors are where they need to be in your dimensional analysis, and we'll talk again about this in a minute. So the mole ratio is converting moles to moles. When we talk about this in the Karate Kid analogy, moles to moles is painting the house. It's side to side. You can go moles of one substance to moles of another substance within a balanced equation. What you cannot do is go from grams to grams that way. Now, molar mass is moles to grams. This is going to be the up down in our Karate Kid analogy. So, molar mass will allow you to convert from moles to grams. Again, if you're struggling with this, go back to the Molar Conversions vodcast, rewatch it, come and see me, get some additional help. I will have some molar mass conversion work in the packet that you can complete in order to get you up to speed on that molar mass conversions. And the next is molarity, which is moles in a liter of solution. We'll talk a lot more about that when we get to our solutions in the next unit. Then we talk about molar volume, which is moles to liters. That's moles to 22.4 liters of an ideal gas. Remember, that is only for your gases. So the core step in all stoichiometry problems is going from moles to moles. We've already done molar mass. We've already done molar volume. Now we're looking at going, can you go from the mole of one substance to the mole of another substance? Okay. Then number 4, of course, as always, is to check your answer. Make sure that you didn't miss a step. Make sure that you didn't accidentally go from grams to grams, because remember, look up here, you cannot do that. You can only go moles to grams. So we're going to take a look at what is called a mole map. And this is really just to show you how the moles are really the center of everything here. So remember that we can convert from grams to moles, and that is by using our molar mass. We can convert from grams to moles or back to grams. We can also convert from moles to number of particles, and that's using the 6.02 times 10 to the 23rd. And that's atoms or ions or molecules, any particle number. That's how many of those particles are in a mole. And then we can also convert 2 liters of gas at standard temperature and pressure, and that is 22.4 liters, which we can convert from moles. So for example, if you want to convert from grams to liters, you would need to go grams to moles using molar mass, and then you would need to go moles to liters. There's no connection between grams and liters. Do you guys see that there's not a connector here between atoms and liters? But you have to go through the moles into this. So moles are there in the center of this whole conversion chain. Then we're going to add one thing that we didn't cover when we did molar conversions, which was that you can do a balanced equation where you can convert from moles of one substance to moles of another substance, the way we did for 2 moles of hydrogen and 1 mole of oxygen. So you can use that mole ratio to do the balanced equation. Okay. And we're going to use this Karate Kid scenario to take a look at this. And I'm going to use the same equation that I used before and use it as an example with this Karate Kid example. Okay. Okay, and I'm going to turn on my drawing pad here, and I hope you will bear with me. I'm just learning how to kind of write on this thing. So we're going to start off with the equation that we just looked at, which was hydrogen gas and oxygen gas reacting to form um, dihydrogen monoxide or water. So we have H2 plus O2 reacts to form H2O. Now the problem we have here is that we have an unbalanced equation, and we can't do stoichiometry with an unbalanced equation. So we need to go ahead and balance our equation and put our 2's there, and that balances our equation so that we have the same number of atoms on both sides. So we're following the law of conservation of mass. Now over here, I would like to draw your attention to this house with moles. Now this means that this is the house in Karate Kid, and meaning that we can go from side to side, but we have to be in the unit of the mole. Okay, so we can move side to side here. Now down here we have the fence from Karate Kid, which is grams, liters, or particles. And we can put grams or liters or particles in this row, but we can't move from one side to the other the way that we can on the house. Because remember, the house was side side, the fence is up down, right? So if you have, say, a number of grams here, you can go grams to moles, or you could go moles to moles only up on the house. So you could say 2 moles of water is equal to 2 moles of hydrogen. Then you can go moles back to grams, but then you need to paint the fence, which is up down. Okay, so again, this is similar to the mole map, except for that everything here is your mole. It's the moles in the center. Now, when we do a problem on this template, we're going to fill out what the question is asking here on the bottom. And instead of doing this as the end of this vodcast, what we're going to do is we're going to do some example problems, and we're going to tack that on as a secondary vodcast labeled example problems of stoichiometry. So we're going to do that as again, we might have 2 or 3 example problems that I will work out and use those as separate vodcasts because we're just about out of time. So look forward to those vodcasts, as well as for some example problems that we'll do as demos within the structure of the class. So you do need to know how to set up this Karate Kid demonstration. So you need to make sure that you put your problem across the top, your equation across the top, put your moles, and put your grams, liters, and particles, fence, and then your question on the bottom. And we will set up some of those equations in our next podcast. Thank you very much, and we'll see you in class.